Hello everyone, welcome back to the third lecture of week 11. As we have explored the concept of the different integrals as the antiderivative as well as the limit of sum. Now it's the time to use some of the terms which are going to use in a different integrals. Most of the terms are analog to the functions we had already known in a calculus, but here are the two special functions. We call it gamma function and beta functions, and their relations between gamma and beta function as well as their individual properties which will help me to evaluate the different integrals in a very quick sense. So, using those gamma function and beta functions, you can evaluate the different integrals of a given complex function in an easiest way, right. So, let us start with the history of the or basic of the gamma function as well as the beta function. As its name suggests, the gamma function has been started by Swiss mathematician Leonhard Euler in 18th century. Gamma function is nothing but it is believed that it is the extension of the factorial functions. So, most of the problems you will see including the gamma functions whenever the gamma function will present is using the factorial notations, right. So, gamma function is an extension of the factorial function of a real numbers, and beta function as known as the Euler's integral of the first kind. Beta function is nothing but it is the Euler integral of the first kind, is closely connected to the gamma function, which itself is a generalization of the factorial function, right. Both beta and gamma function are very important in calculus, as complex integrals can be moderated into simpler form using beta and gamma function. So, now we had a definition of a gamma function. We define a gamma function as a gamma n. Look at the symbol of this gamma n is equal to the semi-infinite integral 0 to infinity e to the power minus x, x to the power n minus 1 dx, right. So, that is the gamma function. Gamma function is nothing but it is the semi-infinite integral e minus x, x n minus 1 dx, right. So, with this definition can we evaluate gamma 1? Let us try to evaluate gamma 1 first. Gamma 1 is equal to 1. How I can prove this one? So, gamma 1 can be written as 0 to infinity e minus of x, x 1 minus 1 dx, right. So, this will comes out 0 to infinity e minus x dx, right, because this will become x to the power 0 is equal to 1, and that will give me, you have to evaluate not in that way, but since semi-infinity or infinite integrals always has to evaluate it in a different way. Firstly, you have to find out some limit a tends to infinity, and then you have to evaluate 0 to a e minus x dx. That is the right way to evaluate this one. So, what will be the value? The 0 to a, so this will gives you limit a tends to infinity, and what will be the value of e to the power minus x? E to the power minus x of minus 1, right, and this will be 0 to a, and this is nothing but this will going to be 1. So, that is how you have to evaluate the semi-infinity or infinite integrals. Here there is a one way, but this way is not very appreciable. You can use for a quick solutions, but that solution is not going to be a conceptual. Here what we have given? We have given a, and taking a as a infinity, that will give me the semi-infinite integrals. So, obviously gamma 1 is equal to 1. Similarly, can we evaluate gamma half and gamma minus half? So, let us start with this one, gamma half. So, put all those values. So, gamma half is equal to 0 to infinity e minus x, x 1 by 2 minus 1 dx, x 1 by 2 minus 1 will become x minus of 1 by 2 dx, right? Indices of this one, right? So this will give you 0 to infinity and putting x equal to t square. So once we put this x equal to t square, that means this dx become twice t dt, right? Remember this one. So e minus of t square and t minus become x to the power minus half, x to the power minus half will become t square to the power minus half. This will become t minus 1, right? So this will become t minus 1, e minus 1 become e minus t2, and that dx become 2t minus t dt. So it's a very easy, integration. Even though it is a semi-infinite integration, but we can find out the integration right now. So this will become t minus 1 2t dt, and tt is cancel out, tt is the cancel out. So this will become 2 is the outside of this integral sign, because it's a constant one, and this will become 0 to infinity e minus 2t dt. And I hope you have remembered this one, that 0 to infinity e minus x square dx is nothing but root pi by 2. And using this one, this will become twice into root pi by 2. So 2 to cancel out, and this will become root pi. So that's the easy way to evaluate gamma half equal to root pi. Now can you try for t minus gamma of minus half? I believe that you will, and you will find out that this is minus of twice root pi. So this will be your assignment here, just to go through it, and you will find out the answer. Similarly, prove that t of n plus 1 is equal to ntn. So this is the recurring type of things. You will find out the nth gamma function, then n plus 1th gamma function is in the nth gamma function, n plus 2 gamma function is nothing but n plus 1th gamma function, and so on. So this is also called reduction formula for gamma n, right? Reduction formula for a gamma n. Now with the definition of a gamma function, let us start with the gamma n plus 1. So how I can write this one? As you remember this one, gamma of n is equal to 0 to infinity e minus of x to the power n minus 1 dx, right? So putting the value of in place of n plus 1, this will give you 0 to infinity e minus of x, and n minus 1 become n plus 1 minus 1, that's become n dx. So that's what it become. And now take this by integration. Take as a u and v two different function. One is exponential and another one is algebraic one. And this will gives you xn e minus x dx. Use the part of integration actually, n into gamma n, and this will become 0 to infinity e minus x n minus 1. Similarly, so this will become 0 and n gamma n here, this will become. So this will come right now as gamma n plus 1 is equal to n into gamma n. So that means the reduction formula has been proved easily by using the definition of the gamma function itself. Similarly, this is the another form of a gamma function, so that 0 to infinity e minus kt t n minus 1 dx is equal to gamma n divided by k p power n, right? So here gamma n has been the definition as 0 to infinity e minus x n minus 1 dx, right? And now using the different formula, so this will become gamma n by k power n is equal to 0 to infinity e of minus kt or kx, you can use this one, kx x to the power n minus 1 dx, right? So how we can do that? That will be this is dt, right? This is dt. How we can do that one? That will be quite easy to prove this one. So let have the left hand side. So gamma n has been written into this one. This is the t. So now t, put the t equal to kx, and dt become k into dx. So gamma n is equal to 0 to infinity e power minus kx, kx into n minus 1 k dx, dt equal to k dx. These are the typo, you have to be careful for these typos. Gamma n is equal to now took from here kp power n common in the I mean break outside of the integral sign, and this will become 0 to infinity e p power minus kx into x p power n minus 1 and dx. This k and this k n minus 1 become kn, and it is nothing but this is gamma n, right. So, this will become gamma n divided by k n minus 1. You have to evaluate this one. So, I have to evaluate it like this. This will taking like in the left hand side. So, this will gives me gamma n divided by k into n, and that is equal to integral sign 0 to infinity e minus of kx into x n minus 1 dx, and that is what it has been asked. So, gamma function has the different form depending on which form is going to be useful for you. Extension of a gamma function from factorial notations. Now case 1. So, what we are doing, we are taking the extension of gamma function from the factorial notation. So, we are going to use factorial notation much more time. So, when n is positive integer, any gamma n plus 1 is equal to gamma n, right, n into gamma n. So, right now we had reduction formula, and that was the reduction formula, see here, and we had proved this reduction formula quite easily by the using the definition of a gamma function. So, gamma n plus 1 is equal to gamma n into gamma n. So, using this one, gamma n plus 1 is equal to n into gamma n. Now, this gamma n can be written as n into n minus 1 gamma n minus 1. This gamma n minus 1 can be written as n into n minus 1 into n minus 2 into gamma n minus 2 and so on. So, using the so on, you will find out n into n minus 1 into n minus 2 into so on 3 to 1. So, this is nothing but factorial n. So, indeed we have gamma n plus 1 is equal to gamma n, factorial n. So, we have factorial n. So, that means factorial 1 equal to 1, factorial 2 is equal to factorial 1, factorial 3 equal to factorial 2, and factorial 4 equal to factorial 3, etc. Right. Now, when n is a positive rational number, that means 2 by 3, 4 by 3 and so on, then gamma of n is equal to n minus 1, n minus 2 up to a positive number in gamma function. A simple way to do this, gamma 7 by 2, that is equal to gamma 7 by 2. So, I can write this one 7 by 2 minus 1 into 7 by 2 minus 2 into 7 by 2 minus 3, and this will comes out to be half. So, this will comes out to be gamma half, and we all know 7 by 2 minus 1 equal to 5 by 2 into 7 by 2 minus 3 equal to 3 by 2 and into 1 by 2 and into gamma of half. Gamma of half we know, gamma of half is equal to root pi. We have evaluated it. Let me show you where here. You see here, we have evaluated this one, gamma half equal to root pi. So, the known up to a known gamma function. So, that will give me 15 by root pi into root pi divided by 8, and that is our answer, right. So, gamma 7 by 2 is nothing but 15 by 8 root pi. Similarly, you can evaluate gamma 4 equal to gamma 4 minus 1, 11 by 4 minus 1, 11 by 4 minus 2 and gamma 3 by 4, because you have known the answer. So, 3 by 4 can be obtained from the table of a gamma function, and that will be your answer. Now, similarly, when n is negative rational number, so gamma n plus 1, using the gamma n plus 1 equal to n gamma n, that is the reduction formula. So, we are going to use this reduction formula, and gamma n can be evaluated from here. Gamma n is nothing but gamma n plus 1 divided by n, and gamma n plus 1 is what? Gamma n plus 1 is equal to n plus 1 into gamma n plus 1. So, we have multiply and divide by the same number n plus 1. So, this will give you gamma n plus 2 here, see, by using the reduction formula divided by n into n plus 1. Similarly, this will also going to be gamma n plus 3 divided by n into n plus 1 by n plus 2. So, that means this gamma n function is now become gamma, continuing this one, gamma n plus k plus 1 divided by n into n plus 1, n plus 2, n plus k. So, using this formula k and k plus 1. So, here the k and this one will become k plus 1, right. So, gamma n can be now written as gamma n plus k plus 1 divided by n into n plus 1 into n plus 2 till n plus k only, right. So, where k is the least positive integer such that n plus k plus 1 is greater than 0. Now, we are going to evaluate this one. So, since it says about n is the negative rational number, remember this one, it is not a negative integer, it is not a negative something, it is a negative, not a negative irrational number, but it is the negative rational number. So, let us take one example that how we can evaluate gamma minus 3.4. So, similarly minus 3.4 plus k plus 1 divided by minus 3.4 minus 2.4 till minus 3.4 plus k, and how much time till it becomes 0. So, minus 3.4 plus k plus 1 become greater than 0. So, k, how much the value of k? K is greater than 2.4. So, what will be the value of k? K is an integer, right, positive, least positive integer. So, how much of k which is greater than 2.4 and the least positive integer is equal to 3. So, this will become gamma minus 3.4, I knew the k. So, gamma minus 3.4 plus k plus 1 divided by gamma minus 3.4 into minus 2.4 and so on till which that till minus 0.4, right, it becomes 0, minus 0.4. So, this number, right. So, that will become gamma 0.6 divided by minus 3.4 and so on, and using the table you can find out gamma 0.6. We have calculated for gamma 0.6, that means 6 by 10, 6 by 10, that is also equal to 3 by 5. You can use the rational one here in the case when n is a positive rational number, that was the formula, right. You have to take n minus 1, n minus 2 till up to the known gamma function. So, that is how we have to calculate for a known positive rational number. So, using that one we can find out gamma 0.6 and the denominator is just a multiplication and product. Similarly, can we have when n equal to 0 or negative integer, can we define the gamma function? The answer is no. So, we have a gamma function for positive integer, for positive rational number, negative rational number, but we cannot evaluate for n equal to 0 or negative integer, right. And these are the calculations you can find out that you cannot be find out for 0 or any negative integers. So, these are the some of the examples. Let evaluate the following integrals 0 to infinity e x square x 2n minus 1 dx. Since this week is going to explore the different integrals. So, gamma function, now the different integral has been given, but the lower limit and upper limit are quite different things. Lower limit is 0 while the upper limit is infinity. That means we have some semi infinite integrals. In that case you are going to use the gamma function or beta function. Later on we will introduce the beta function as well. So, here we have to evaluate 0 to infinity e x square x 2n minus 1 dx, n is greater than 1, right. So, we knew that gamma n can be written as e power minus t power n minus 1 dx. Putting t equal to x square and it will become gamma n equal to 0 to infinity e minus x square x2n minus 2 into 2x dx, and doing the whole calculation it will comes out 0 to infinity e x square x2n minus 1 dx, right. And this is nothing, as you can see here, this is gamma n divided by 2. So based on this problem, as you can see here, how much the value we have find out here. We have find out for n is greater than 1, this will become gamma n by 2. So half gamma n, right. Based on those, can you evaluate the integration of 0 to infinity e root x x to the power 1 beta 4 dx. So can you write down this one as minus 1, right. So you have to write down 0 to infinity first, e of root x or x to the power 1 by 2 x to the power 1 beta 4, that can be written as minus 1. So how I can write this one? So see, n into n minus 1 equal to 1 by 4, n can be written as 1 by 4 plus 1 equal to 5 by 4. So x to the power 5 by 4 minus 1 dx, right here, and evaluate by using the formula directly, e to the power k into x and so on, right. We have done this one, so you can use directly. Similarly here, as you can see, 0 to infinity a to the power x x to the power a dx. What you have to do? We have to evaluate a to the power x as the exponents function and so on, right. Similarly use this one. So I am going to left for you and just treat this one as the assignment of this week. Now we are going to define the beta function. As in the initially we have coined two terms, that was the gamma function and the beta function. Here is the beta function has been evaluated and explored. Now we have here a beta function. So beta function is defined as beta mn, and 0 to 1, this is the different integral from in a closed interval 0 to 1. 0 to 1 x to the power m minus 1 1 minus x to the power n minus 1 dx mn is greater than 0. You can change this one, that means it is a very symmetrical one. So this beta 1 relation between beta function and gamma function is this one, right. How we can find out the relation? Very easily to do this. At this moment I am going to left for you, but it's very easy to do this. Now we are interested to find out beta mn is equal to beta nm or not. What do you think? See, changes anything in place of 1 minus x to x, nothing has to be changed. So both are the symmetrical one. So beta function is symmetrical, beta mn is nothing but beta nm. And how to prove this one? Let me prove for you. So by the definition, beta mn is 0 to 1 x to the power m minus 1 1 minus x n minus 1 dx, where m and n both are greater than positive number. And this can be written as 0 to 1 1 minus x m minus 1 1 minus of 1 minus x n minus 1 dx, right. So I have placed this x as 1 minus x, this place as well as 1 minus x. It has nothing to do with this one, and this will comes out what? This will comes out to be here, as you can see here, this will be x to the power n minus 1, and this will comes out to be 1 minus x m minus 1. Now this x n minus 1, see here it was the x m minus 1 and here x n minus 1. So the things has been changed, not like this, but things has been changed as nm, right. So this is the typo, you have to just ignore it. So we had proved this one, beta mn is equal to beta nm. So beta function is symmetrical. Similarly, we can explore the another form of a beta function. Beta function can be written as 2 into 0 to pi by 2 sine 2m minus 1 into theta cos 2n minus 1 into theta d theta. This is quite important sometime when geometrical problems come in the picture, and some of the different integrals where you need 0 to 1 evaluation or so on, and you need a beta function. So that is how we use this another form of a beta function. How to prove this one? Very easy to prove this one. Putting x equal to sin square theta and evaluate dx and d theta, and putting back to the whole integration, it will gives you the beta function. So let me do this. So beta mn is given 0 to 1 x to the power m minus 1 1 minus x n minus 1 dx, where m and n both are positive numbers. So now let assume x equal to sin square theta. So dx equal to 2 sin theta cos theta d theta. Now putting back to here, so beta mn is equal to 0 to 1 x to the power m minus 1 into 1 minus x to the power n minus 1 into dx, right. So this will be x, the value of x equal to here, I have changed this one as x equal to sin square theta. So sin square theta, and this to the power m minus 1 into 1 minus of x, this will 1 minus sin square theta. So this will become cos square theta, and this will become n minus 1, and dx can be written as twice into sine of theta into cos of theta d theta. Now evaluate this integral. This will comes out to be 2 is here. So taking outside of this 2, this will become it has to be changed here, right. So this one is not 0 1, but it's become 0 to pi by 2. See here, x equal to 0, this will come sin theta, theta become x equal to 0, theta becomes 0, x equal to 1, theta become pi by 2. So that's how we have to evaluate this. So this form is equivalent to the previous form, right. So the beta function can be retained in a trigonometrical function sin 2m minus 1 theta cos 2n minus 1 theta d theta and so on. These are the results from the another form of a beta function is given by beta mn equal to 0 to infinity x to the power m minus 1 1 plus x m minus 1. And how to prove that one? Put the appropriate x equal to this function, and you will find out that the form is coming out in a right way. Similarly, this is the another form, and by evaluating beta mn, thus beta mn can be written as gamma p plus 1 by 2 gamma q plus 1 by 2 twice of gamma p plus q plus 2 divided by 2. And similarly, this is the another form, and the relationship between the gamma and beta function. So evaluate using those one, evaluate 0 to 1 x square divided by a square root of 1 minus x to 5 dx. Let putting the y equal to x to the power 5, we have dy equal to 5x to the power 4 dx, and I can be written as 1 by 5, 0 to 1 y minus 2 by 5, 1 minus y minus 1 by 2 dy. Minus 1 by 2 can be written as 1 by 2 minus 1. So here we have changes this. Minus 2 by 5 can be written as 3 by 5 minus 1. So we have changes it here. So now this will be nothing. You don't need to evaluate this function, but this function is in the beta function can be written as this integral is nothing but 1 by 5 beta of mn that is equal to 3 by 5 1 by 2. No. And this answer can be also symmetrical. So this can be written as 1 by 2 3 by 5. So both are exactly the same answer, and both are true. Now another example, evaluate I equal to 0 to pi by 2 sin q theta cos pi by 2 theta d theta, and you knew the answer, right. You knew from the different another form of the beta function, and by using this one, beta mn equal to 0 to pi by 2 sin p theta cos q theta d theta is in the gamma function. So you can write directly here p equal to 3 and 5 by 2. You can write this one as p and q. So here is the p and it's the q. So gamma p plus 1 by 2, gamma q plus 1 by 2, and so on, 2 into gamma p plus q plus 2 divided by 2. So it will gives you 8 by 77. So now you can see and you can visualize the whole things that using the gamma function or beta function, the integration become more easier to solve, and it become in such a form where you can apply directly the given results of the gamma and beta function. That integral values can be evaluated quite easily. And okay, so we have taken the last problem for you, that is I find out the integral I 0 to pi by 2 sine 10 theta d theta. So sine 10 theta d theta can be evaluated using the same thing, right? So I have taken that sine of 10 theta and 1 by 2 and so on. I mean, you can have the cos of 0 and so on. So you can go through the another form of this one, right? See, so we have used this formula. So using those formula, we have a gamma 11 by 2, gamma 1 by 2, 2 into gamma 6. What we have do, we have retained in such a way that sine of 10 of theta and into 1 into d theta, I can write this one. And we knew that how I can find out this value. So see here, so sine p theta cos q theta. So now you can put this one 0 to pi by 2 sine of 10 theta into cos of 0 into theta d theta, right? So p equal to 10 and q equal to 0, right? That is how you can evaluate. So you can evaluate gamma p plus 1 divided by 2 into gamma q plus 1 divided by 2 divided by twice into gamma p plus q plus twice divided by 2, right? That will give you gamma 11 by 2 into gamma 1 by 2 divided by twice into gamma 6. And what will be the answer? The answer is 945 by pi divided by 7680. Now you can imagine that any integral in a trigonometrical form which is can be reduced in a beta of functions can be easily evaluated using the properties of the beta function or another form of the beta function. I believe that this will help you to find out the integral functions of a complex functions, integral values of the complex functions, and wherever you want to use the beta function and the gamma function as the integral value, you can frequently use that one. So this one will be your assignment and try for this one. Thank you so much.